In the early days of the jet age, engineers hit a wall. Sir Frank Whittle, the father of the jet engine, faced a problem that threatened to ground his invention. The steel alloys available in the 1940s simply couldn't take the heat. As engines ran, turbine blades would soften, elongate, and fail within hours. They realized that to fly faster, they didn't just need better aerodynamics, they needed to rewrite the rules of metallurgy. Today, inside a modern jet engine, conditions are indistinguishable from hell. Temperatures scream past 1,500 degrees Celsius. To put that in perspective, at this heat, structural steel turns into jelly. Titanium catches fire. Aluminum would vanish instantly. Yet buried deep inside this inferno, spinning at thousands of RPM, there are components that don't just survive, they thrive. They are made of Inconel. It is the material that conquered the heat barrier. But it is also a material so difficult, so expensive, and so frustrating to work with, that machinists simply call it a nightmare. We usually think metals fail by snapping or melting. But in high-performance engineering, there is a much scarier way to fail. It's a silent killer called creep. Imagine a turbine blade. It's spinning at 10,000 RPM, pulling outward with centrifugal force equal to hanging a school bus from the tip of the blade, all while being roasted. Under these conditions, ordinary atoms start to panic. The atomic bonds loosen. Slowly, invisibly, the metal begins to flow like cold honey. This is creep. If a turbine blade stretches by even a fraction of a millimeter, it touches the engine casing and boom! The engine destroys itself in a shower of sparks. Most metals surrender to this force. Inconel was designed to fight back. Inconel is not a single metal, but a family. There is Inconel 625, the master of corrosion resistance, and the legendary Inconel 718, the workhorse that makes up nearly half the weight of a modern jet engine. At their heart is nickel, but nickel alone is soft. To toughen it up, engineers add chromium for a shield against corrosion, and specific amounts of molybdenum, niobium, and titanium. But here is the real magic. It happens during heat treatment. When Inconel is heated and cooled strictly, these elements combine to form a specific microscopic phase called gamma prime. Think of the metal like a stack of slippery paper. The gamma prime particles act like tiny cubic nails driven through the stack. They pin the atoms in place. They create barriers that stop the atomic layers from sliding over each other. This is known as precipitation strengthening. While other metals are sliding apart internally, Inconel remains locked solid. It doesn't just resist heat, it ignores it. But as engines got even hotter, even Inconel began to creep at the edges. Engineers realized that metals are usually made up of billions of tiny crystals, or grains. The borders between these grains, called grain boundaries, are the weak spots. They are the microscopic cracks where the metal begins to slide and fail. So engineers asked a crazy question. What if we remove the boundaries? What if we make the blade out of one single crystal? This led to the invention of single crystal casting. The process is ingenious. Molten Inconel is poured into a mold, but at the bottom, there is a corkscrew-shaped passage called a pigtail selector. As the metal solidifies, billions of crystals try to grow upward. But the spiral shape acts like a filter. It kills off all the competing crystals, allowing only one lucky crystal to survive and grow into the main mold. The result is a turbine blade with effectively zero grain boundaries. It is one continuous, uninterrupted metallic diamond. This technology alone allowed jet engines to run hundreds of degrees hotter, dramatically increasing fuel efficiency. Now let's clear up a common misconception. Is Inconel the strongest metal on Earth? The honest answer is no. If you test them at room temperature, many high-strength steels are actually stronger. They can handle heavier loads before bending. But strength is not a universal constant. It is a slave to temperature. Imagine a graph. As heat rises, steel falls off a cliff. By 600 degrees, it's useless. Inconel, however, refuses to give up. It retains a massive portion of its strength even as the thermometer hits the red zone. Engineers don't choose Inconel because it's the strongest metal everywhere. They choose it because it is the strongest where it matters most. But even Inconel has limits. In the most advanced military and commercial engines, the gas temperature can actually exceed the melting point of the metal itself. Wait, let me repeat that. The air is hot enough to melt the blade, yet the blade survives. How? It cheats. Advanced Inconel blades are not solid. They are hollow. They feature intricate internal channels that route cooler air from the compressor through the metal, acting like a built-in radiator. This cooling air bleeds out through rows of tiny laser-drilled holes on the surface, creating a protective film of air. It's like the blade is wearing an invisible suit of armor made of cold air. The blade survives not because of material science alone, but because Inconel works in harmony with fluid dynamics. So if Inconel is so good, corrosion-resistant, heat-proof, super strong, why don't we make engine blocks or suspension bridges out of it? Because manufacturing it is absolute hell. When a cutting tool bites into Inconel, the metal doesn't just cut away. It reacts. It undergoes work hardening. The stress of the tool causes the metal surface to instantly become harder and stronger. Imagine trying to cut a steak, but the moment your knife touches it, the steak turns into stone. It destroys cutting tools in minutes. It generates intense heat. It forces production to move at a snail's pace. Often, traditional cutting is impossible. Manufacturers have to use EDM, electrical discharge machining, where they use sparks of electricity to vaporize the metal instead of cutting it. It is slow, energy-intensive, and wildly expensive. This difficulty has actually sparked a revolution. Since cutting Inconel is so painful, modern aerospace companies like SpaceX and Relativity Space started asking, what if we don't cut it at all? They are turning to additive manufacturing or 3D printing. Using lasers to fuse Inconel 718 powder layer by layer, engineers can build shapes that are impossible to machine. They can print those complex cooling channels directly into the walls of a Raptor engine combustion chamber, curving and weaving them in ways a drill bit never could. This doesn't just solve the manufacturing problem, it unlocks geometries that were previously the stuff of science fiction. Inconel is not magical. It is the result of decades of metallurgical science, continuously refined to push the boundaries of physics. It is heavy, costly, and stubborn. But in a nuclear reactor, a chemical processing vat, a rocket nozzle, or a jet turbine, reliability is the only thing that matters. Inconel stands tall where other materials wither and die. If something flies, burns fuel, or operates at the edge of the impossible, there is a strong chance this superalloy is playing a quiet but essential role inside it. Please like, share, and subscribe to my channel, Decoding Everything. Visit Decoding Everything for more amazing and interesting content. Thanks for watching.